welcome back. In the last class, we went through Legendre transformation in order to change the variable and such that we retain the information of the properties. So, what we are going to do is we are going to apply Legendre transformation thermodynamic functions. Okay. So, I will just start with u as a function of u s v n, okay. And what we are interested is we will apply Legendre transformation with respect to s. So, that means we can get a function u minus s times derivative of u with respect to s, keeping all other things constant. Now, knowing that from the differential or the derivative relation of u is d d s minus p d v plus mu d n for pure system. So, from here we can see that partial derivative of u with respect to s is nothing but t. So, this is equivalent to u minus T s. So, now we can define this as another function which we call it a. All right. Now, a is nothing but we say this as Helmholtz potential or function. Okay. If we take a derivative or relation of this, this is going to be dA is equal to du minus T ds minus s dt. Okay. We can plug in this expression of du here and we can show this as minus s dt minus p dv plus mu dn, okay. And thus this is nothing but a function of v n and t, okay. So, we have converted s variable to t v n by taking the Legendre transformation with respect to s, okay. So, for this function t v n is a natural variable, okay. Similarly, we can also do Legendre transformation of this with respect to v, and in that case it is going to be u minus v times the derivative of u with respect to v, okay. And from this expression we know that del u by del v is nothing but minus p, okay. So, that is u plus p v, okay, and this is nothing but, so this goes this turns out to be u plus p v, and this is nothing but our enthalpy, which is a function of s p n, okay. You can see this by getting in a derivative relation. This is going to be dh is du plus p dv plus v dp. You make use of the expression of u, and thus you can get t ds plus v dp plus mu dn, okay. And thus this is a function of s p n, which is a natural variable for enthalpy. We can also try to do successive transformation of u, successive transformation of u, Legendre transformation of u with respect to s and v, okay. So, either we do successive Legendre transformation of u with respect to s and v, or if we do single Legendre transformation with respect to v, or single transformation of h with respect to s, we get the following expression u minus T s with respect to s minus u minus T s plus p v, okay. So, this is the first transformation, this is the second transformation, or this would be your A transformation with respect to V, or you can consider U plus PV and take this H transformation with respect to S will lead to the same expression, and this we call it G. This is same as A plus PV or H minus Ts. Okay. All right. So, you can get a derivative relation as M minus S dt plus V dP plus mu dN. Okay. So, this is how we derive the thermodynamic functions of, in order to get potential functions which depends on different natural variables. So, what we have done is we have taken internal energy which is a function of S V n and converted into different functions which depends on different variables which are more important or relevant for experimental conditions. So, let me make use of Euler integration to come up with another expression. So, I will start here with du as TdS minus PdV plus summation mu I dNi for multi-component mixture, and using if Euler integration we can come up with this expression U as Ts minus PV plus summation mu I Ni. Okay. Now, here if you take a derivative, so this is an du TdS plus S dt minus PdV minus VdP plus summation mu I dNi plus Ni d mu I. Now, using this expression, so this is let us say 1, this is 2, and using these two expression you can derive the following, which means 1 and 2 yields S dt minus VdP plus summation Ni d mu I should be 0, because both this expression holds and thus this relation should exist. This leads to an extremely important conclusion, which is that for any change of state, okay, having n plus 2 intensive variable, T, P and mu I, where I is equal to 1 to n, where n is number of components, it tells you this expression, which is also called Gibbs-Duhem equation or relation. So, it tells you this that n plus 2 intensive variable cannot be independent. So, this cannot be varied, cannot vary independently. Okay. It also tells you that since this is a constraint which is being put, it tells you that n plus 1, only n plus 1 variables are independent, can vary independently. Okay. Now, this expression is important for degree of freedom analysis and consistency check with experimental data. Okay. So, having derived this expression, which is or which are thermodynamic functions, okay, let me just summarize these auxiliary functions corresponding definition and as well as the derivative and natural variables. Okay. So, you have this enthalpy, Helmholtz free energy and Gibbs free relations are U plus PV is U minus Ts and G is H minus Ts. Okay. And the corresponding derivatives are dH is TdS minus VdP plus summation mu I dNi. Okay. What are the natural variables here? S, P, Ni. Okay. Similarly, for dA is minus S dt minus P dV plus summation mu I dNi. The natural variables are T, V and Ni, and for G you have del dG is minus S dt plus V dP plus summation mu I dNi, and natural variables here is T, P, Ni. Okay. These thermodynamic functions which we have derived plays an important role in many applications. One thing we should understand that these functions plays a direct role in equilibrium conditions for a given, for their own natural variables for that matter. Let us assume that if you are talking about Helmholtz free energy A, it means that A is going to be minimum at equilibrium for a given temperature, volume and amount of the substance. Okay. Similarly, Gibbs free energy also plays an important role for condition, temperature, pressure and amount of substance. When it is kept constant, G is going to be minimum. Let me just go through this briefly, this importance of this thermodynamic function and its role in analyzing the equilibrium, okay, for specific set of variables which are kept constant. So, if we let us go back to the case of S V n, okay, and for such a variable fundamental equation or natural u is a fundamental thermodynamic function for natural variable S V n. Okay. The consequence of second law is that that S is maximum at equilibrium, okay, for given u v n. Okay. Now, in other words, S as a function of time, it continuously increases until it reaches a equilibrium values. Okay. So, second law tells you that del S is going to be greater than or equal to 0. Okay. So, this also implies that u is going to be minimum for given S V n. Okay. So, let me just try to explain. So, we can consider the first law, okay, and we know that change in the entropy of the system is greater than or equal to del Q by T, where T is basically nothing but the temperature of the reservoir or the bath. Okay. So, this is for reservoir or bath. Okay. So, I can rewrite this expression as del W is equal to del Q minus du, which is nothing but T ds minus du, or I can write du less than T ds minus del du. Okay. So, now if du is constraint, if du is constraint at constant S and V, this implies that du is going to be less than or equal to 0. Okay. So, what it says that at constant entropy and volume, u tends towards minimum in an actual or irreversible process in a closed system, and it remains constant in a reversible process. So, in other words, it provides this expression provides a criteria for equilibrium, that means du less than or equal to 0 or u tending towards minimum in a closed system provides an criteria for equilibrium system. We can make use of this analysis also and extend it to the different free energies. So, I will take an example. So, instead of deriving it, I will just make a statement here that similarly we can try to show one can show that dA is less than or equal to 0, okay, is a criterion of equilibrium of a system enclosed in a rigid container held at a constant t. It basically means is a TVN is basically the variables which is kept constant. That is, what we are saying is basically A will reach minimum at equilibrium for a given TVN. Okay. Now, similarly, you can show also that G, the Gibbs free energy, will reach a minimum for a given TPN. Okay. So, similarly, now, this particular condition of constant temperature and pressure are of greatest importance to practical conditions, because this is what you maintain in laboratory, and thus this dg greater than or dg less than equal to 0 or the condition for equilibrium plays an important role in phase equilibrium and reaction equilibrium analysis. Okay. Now, in addition to G, A also plays an important role, because you can also maintain temperature, volume and then constant in a closed rigid container. So, let me just give a little bit flavor of this understanding of this free energy. So, if we consider, for example, a case where you have a rigid container, okay, where you have maintained the bath at T, and there is a vapor which is can get can condense and crystal can be formed. Okay. Now, in this case, of course, the volume is fixed, temperature is fixed, the overall amount is fixed. So, basically this is TVN. The natural thermodynamic function of potential is A. So, A is nothing but U minus Ts. All right. Now, if we make use of some statistical methods and evaluate in this U and Ts in some way, it turns out that it will look like the following. So, let us say this is 0 and this is your percentage of vapor. Okay. So, as the amount of vapor increases, what we see is that U keeps increasing, okay, whereas Ts increases, but at certain point U is more than Ts, and effectively the A shows a minimum. Okay. So, in other words, A is minimum for a specific value or specific composition of vapor and crystal. Okay. So, we can understand this little bit more by considering that there are attractive forces between the molecules which tends to make the vapor condense. So, if vapor condenses, U tend to decrease, okay, and if U is minimum, S is also low, okay, it is becoming more ordered. On the other hand, if there is a heat being pumped from the bath, S increases, so does U. Okay. So, there is a certain balance between the order and disorder in order to minimize A. Okay. So, the balance between order and disorder in the system leads to a minimum value of A. Okay. In an isolated system, of course, S would have been maximum and U would have been minimum, but considering that in this particular case you have fixed the temperature volume, what it leads that there is a competition between U and T s, which essentially means order and disorder, and thus there is a minimum for a specific value of the vapor. Okay. So, this is how we try to analyze or make use of the free energy, which plays a significant role in understanding the equilibrium behavior of the system. So, with this I will stop. We will continue this exercise in the next lecture.